So thank you for the introduction. So today I will go maybe on the other side, more in the hardware side. I will talking about eAxle system and more especially about the influence of e-motor cooling concept on performance and efficiency. So I will have three main parts in the presentation. First, show you an overview about our e-mobility solution at Bosch. Then doing the cooling concept analysis, so first the influence of the cooling system on the performance. In the third part, I will look at the influence of the cooling system on cycle efficiency, and finally a short outlook about trends and technology for the future. So first, our e-mobility solution at Bosch in the business unit electrified motion. So we are focusing on high voltage electrified solution for all vehicle class. So we provide solution for passenger cars, light commercial vehicle, and heavy-duty commercial vehicle. And our aim is to enable our customer to successfully drive electrified mobility over the entire range of application, and also worldwide with different partners. Looking at the solution we propose, so we want to cover all the applications. So going from semiconductor to electric drive system and charging solution. We are also covering the entire applications from manufacturing to system engineering, and as I said before, for all applications. So we provide solution with silicon carbide semiconductor on the chip level. On the sub-component level, we are providing rotor, starter, and entire lamination solution, but also power module and cooler. On the component level, we are provided inverter and electric motor, and on the system integration level, we are focusing on charger converter, which is having a charger and DC-DC converter on an eAxle system with solution extending from 3-in-1 to X-in-1 with a lot of component in it. Using this approach, we have a lot of standardization because we can reuse the different components on the different level, which is good for economics of scale, and we are also a high level on integration and customization for supplier also on the system level. In this presentation, I will focus on eAxle. As we can see, we have two types of eAxle that we can use in different type of cars. So we have our small eAxle, which is mainly focused on city battery electric vehicle, and we have the bigger eAxle that we can also use for SUV and premium battery vehicle. The small eAxle, using our disconnect technology, can also be used as an all-wheel drive when you can disconnect the gearbox and the e-motor from the wheel to increase the efficiency and improve the range. So before going deeper in the analysis, I will show you the key requirement of eAxle. So first one of the list is always performance. We need to fulfill power, torque, and speed requirements. Second one is integration. The eAxle need to fit in the car from the customer. We need to look at the dimension of the component and the cooling and the technology to fit in this available volume. Then an important topic, as always, is the functionality. Electric drive are well known to don't produce too much noise, so NVH is a big topic. And as I said before, we have also disconnect to increase efficiency and range. After that, a really important topic is the efficiency. We need to understand the component losses to improve the system efficiency. And last but not least, as always, we have the cost. We are always minimizing the cost for maximal performance and trying to find new technology and innovation to go in this direction. So going to the analysis, it's divided in two parts. So first, an analysis of the cooling concept, and then a kind of system optimization considering the advantages of the drawbacks of each cooling system. So it's first a description of the e-motor part that we know is the important part. I think for most of the people it's well known, just that to know which color is which part of the e-motor. And on the right side, you can see the basis design I take as a reference. So we have a machine with a total diameter of 220, a length of 85, a voltage level of 800 volt, and performance is 4,000 Newton meter, 250 kilowatt, with a gear ratio of around 13. If we now take this e-motor part for the reference cooling system, I put everything possible in it. So on the starter side, we will have a water jacket with water cooling, and on the rotor side, we will use oil. we will put the oil through the shaft and have some holes in the shaft to spray oil on the end winding from the bottom to improve the starter cooling. The oil will then collect at the bottom in the oil sump and will be pumped out of the system. And for the analysis of the performance, I will be using the continuous to power ratio. So the big white line will also always be the peak power, which we normalize by the max value, and then we can look at the difference parameter. So for example, in our reference design, we can look at the limit due to copper. So if we consider the maximal temperature of copper, we will have typically this continuous performance for 30 minutes. If we look at the magnet, it will more look like this. And then to find the global performance of our system, we need to combine both lines, and we will have the resulting white line, which is the continuous power of our system. To understand the cooling system and show the impact on the global system performance, I will make several analyses. So first, a separated analysis, when I just cut my cooling system in two, considering the rotor oil cooling separately and the water starter cooling separately. Therefore, we will see the speed and torque dependency on both of them, and then we can understand which part is helping in which case, and to understand the complete system. And on the other side, I will compare this combined water and oil cooling to what we are now looking for. It's a full oil cooling system. So we will just not only cooling the rotor with oil, but also the stator. And by doing this, we can increase the efficiency, reduce the number of components. And when we can even go deeper, we can also go through the spark of the rotor to even going nearer to the component we want to cool. By doing this, we will see the potential for this highly integrated oil-cooled system, and at the end also see the advantages by going with oil and an electrical pump in the system. So here's our reference. We reach approximately 60% of the peak power as continuous power. And if we now look at the different system, removing the rotor oil cooling from the system is making a huge gap. So we have only around 25% of the continuous power using only the water jacket. And when we put only the rotor oil cooling, go to around 30%. So using only one of the two cooling systems, we are really a big loss of performance, but as we will see later, there is some other advantages. If we now go to the full oil-cooled system, we see some smaller disadvantages. We are really near the reference system, but since water is better for cooling, we still have advantages. And if we look at the solution with the direct rotor cooling system, it's showing similar performance. Now we were looking at the max value. Another interesting point is also to look at the speed dependency. So for example, if we look at higher speed, we see that the ranking is not the same anymore. And for example, going with direct rotor cooling in our system, we will really increase the power at max speed, and we are even better than our references. So another topic in this case is always the cost. So if you compare the two curves on the left, you will see that oil cooling, because it's the same machine, just changing the cooling system, it's a little more expensive because instead of having only a jacket on the outside of the starter, you need to put an oil cooling system with a heat exchanger, an electrical pump, and a filter, for example. The reference system is the most expensive one because it has both cooling, so you need both the water jacket and the oil cooling system. And the two systems on the right are only oil cooling. It's a little more expensive with the direct oil cooling system because we need to put the oil through the rotor and add some additional part to drive the oil in the system. As I said before, for the integration, we compare only the same machine. So we have an active diameter of 200 millimeter, and at the beginning I said 220, because in our reference we have a water jacket. So the actual part we need for the machine is the 200 millimeter we use in the electromagnetic simulation plus the 20 millimeter for the water jacket. For the oil cooling, we are only doing oil cooling at the surface, so we will have different cooling concept at the surface of the starter. It does not take as much room as the water jacket cooling, so in total we will have a smaller system, and all the systems are using the same active length. Now, combining the different results, we can see the continuous power over the cost. So we put the normalized continuous power over the cost. And one we can see, it may be also due to the scale, there is a big gap between the reference design system and the other system because it had both the system. It's the best solution. We reach the bigger continuous power, but it's for higher cost. What we can also see is even if the water jacket is having only 25% of the max power, the continuous power, regarding cost, it's still the cheapest solution, the easiest to apply it because you don't need extra oil pump and so on. Going to the continuous power versus integration, we are looking now at the total diameter we required. So using only rotor oil cooling, since we don't need some extra room on the starter, it's a really compact solution. Everything with water would be the biggest one, and the other oil system is between the middle. What is really important in this case is that we are comparing the cooling system and not the total integration. That's what we will see in the second part when we are using this remaining available diameter to check the differences. So going in the second part, we will analyze the differences between the system and adapt the system to use the full potential of the difference cooling. So the second part is about the potential. So we'll go through the different system. That, for example, the detail result of the water jacket cooling. What we can also see is that over the entire speed range we have limiting by the magnet because the reference design is designed for rotor plus starter cooling. So using only starter cooling, we are directly limited by the magnet. And on the right side, we can see the current continuous power we see before. So what we can do to increase it, there is different steps. So first we can, for example, reduce the thickness of the steel in the system. We'll then reduce the iron losses in both starter and rotor, which is helping to reach more continuous performance. It's a big discussion with OEM, but if you really want to increase the system, you can also reduce the coolant temperature. So in the case of the water cooling, we don't have control over the coolant temperature. It's coming from the outside, from the vehicle, but it's always a nice solution. You can have variable coolant temperature over the speed, depending on the cooler performance of the vehicle. And the final, the one no one wants to see is increase the magnet temperature, so increase the maximal temperature. It has a huge effect in this case, since we have no rotor cooling in this system, but it has also a huge impact on the cost. Same analysis we can do for the rotor oil cooling. Here we can see, even if it's only in rotor cooling, we are still spraying some oil on the starter, so we still have a good starter performance. And we are still seeing that in this case we have magnet limiting. We can go through the same step, but in this case we have a first step we can do is increasing the diameter. Since we are not using the full diameter for the cooling, we can use this available space, for example, to increase the active diameter of the electric machine and get some more performance. So in this case, for example, we see a huge gain in the torque at the beginning, but it's also helping for the cooling concept because by increasing the diameter, we can reduce the length in the system and therefore reducing the distance between the hotspot in the middle of the system and the cooling on the side of the rotor. Then as before, we can reduce the steel thickness, also making a huge impact on the cooling. And finally, the solution no one wants to know, increase the magnet cost. In this case, since we already reached the starter limit, increasing the magnet depth has only a big impact on the higher speed level when magnet is limiting. So for the starter and rotor oil cooling, we are already really near the performance. We are still limiting by the magnet at high speed and by the copper in lower speed. We can do the same analysis as before. We can increase the diameter, not as much as before because we still need some room from the oil cooling system on the top. But we have some slight increase, which is increasing the performance. We can increase the magnet temperature, which is helping for higher speed, and go with the steel thickness, which is making a huge gap. So we are currently already over the reference design. Finally, the starter and rotor direct cooling. So as we can see, since we go directly through the rotor hole, we have a really good cooling performance for the magnet, so the magnet are not limiting. Considering only the magnet, we are already over the references. It's more a starter topic, and when we see the different change, we can make it's more than enough to just do the changing in diameter. We are already reaching the similar performance to the references, and then we don't need to put some additional extra cost. So going back to our performance comparison, so that's the results from before. And now if I make one more click, we see the differences. So with some small changing, we can fill the gap between our reference and our oil-based system design. We can also see it on the right, so all the curves are on the same level, considering the max value. We put a lot of effort in the water jacket and in the rotor oil cooling. The rotor oil cooling, you see the difference is not that huge, but in the water cooling, we can almost double the continuous performance. So putting a lot of cost, but also increasing the performance by 100%. And if we go to the higher speed, putting a lot of cost in the full oil cooling system, we are already better than the direct or rotor oil cooling, but everything going in the same direction. So the rotor oil cooling alone already reached the same performance as the reference design. So now the bad news are coming regarding the cost. That's the cost from before that we see from the reference design, and now if I put the changes in the design, we see the increase. So for example, for the water jacket and the rotor oil cooling, we put the additional cost in the machine design or in the boundary condition, and we reach similar cost to the reference design without reaching the same performance. So in the design is always to find a trade-off. Did I put my additional cost in the motor design? Did I put it in the cooling system to find the better solution? For the full oil cooling, we have increase of the cost of the machine, and for the direct rotor oil cooling, we have a slight reduction of the cost because we can adapt the machine to the cooling system. If I zoom in it, because we cannot see it that much in fact, we see that the system with direct rotor oil cooling is less expensive, and we will see on the next slide the differences. So as we said before, we have all machine with same diameter and seeing the influence on the cooling concept. Now we can adapt the design of the machine. So for example, with the rotor oil cooling, we have housing the entire available volume for the electromagnetic part, and for the other oil cooled system, we could also increase the active diameter. And what we also see is that it has a huge impact of the length. So in the rotor oil cooled system, thanks to the additional diameter, we could reduce the length to 72 and around 74 or 75 for the two other oil systems. So the system will be more compact, and also it's helping for the cooling. So now going back to the cooling concept comparison, that's the result for the first design, considering only cooling concept. And now if we put the new system, all the three systems, so the reference system and the two oil-cooled systems, are now on a line, and the only difference is the cost. What we see is that for the system with direct rotor oil cooling, we could reduce the cost, while in the other one we increase them. And what is really important is that the water jacket, even if it had past performance, it's still a cheaper solution if you don't need this higher continuous requirement. So it's still kind of like of the Pareto front. If you need a cheap and easy solution and you don't have high continuous requirement, you can still go for the water jacket. If you want to find the best compromise between continuous power and cost, you can go with this highly integrated oil-cooled system. Now regarding the other side, instead of comparing the active diameter, I will now compare the active volume. So that's the result from before. And if we put the new design, it does not make a big changes. So the rotor oil-cooled system is getting bigger, because even if we reduce the length, we have a huge increase in the diameter, which is increasing the active volume. So we are still smaller than the references, but to reach this higher performance, we still need a bigger volume. And therefore, considering integration, the rotor oil-cooled system is still the most compact system, but it's not the best compromise between continuous power and available space. So what we can see in this analysis is that The single cooling system cannot reach the requirements. They are kind of optimum regarding cost for the water cooling and regarding installation space for the rotor oil cooling system. But if we really want to reach high continuous power in a small available volume, we need to go for this highly integrating oil-cooled solution. By doing this, we also have some other advantages for the efficiency. So that's why we will look on the other part. So we will look at the influence of the cooling system on the cycle efficiency. For this, we take typical cycle in Europe. So VLTC, e-motor design is the same as the first part of the analysis. We take the same e-motor and only change the cooling. Therefore, we will use our temperature model also for cycle evaluation. So e-motor, all the temperature in the system will be calculated. Inverter, we take a constant temperature because on the VLTC, the influence of the temperature is not that much on the inverter. And for the transmission, we do two different cases. So if we use an oil cooling in the rotor, for example, the oil would be heated up by the e-motor, going then to the transmission. Therefore, we'll use the output temperature of our temperature model from the e-motor for the transmission. And if there's no oil cooling in the rotor, we'll use the same temperature of the electric machine shaft because she's directly connected to the transmission. So that's our reference system, just making bigger. And if we look at the different system, we'll see no big differences on inverter and transmission level. The big differences we see is on the e-motor level. We have no oil cooling, and if we just blind and go with the full oil cooling during the entire VLTC, we have a lot of oil in the system, doing additional drag losses in both the transmission and the e-motor, and therefore the water jacket, which was not the best for the cooling system, is not the best for efficiency because we have a dry rotor in the system, and therefore we have no additional losses and we have lower friction losses. If we look at the different cooling system, just zooming in, the difference after the digit is really small, but we still see differences. And in this case, going with full oil cooling, the differences are really slow. But if we see, the best system is the one with the water jacket and the rotor oil cooling. And what is it like this is that there is different relationships. So the different part in the motor, some want to be hot, some want to be cool, depending on the losses, and therefore having this oil cooling system, we can control this. So what I will show on the next slide is first a theoretical analysis. So for example, the starter, it's kind of trivial. We have ohmic losses. They are dependent on the temperature. So over the entire speed and torque range, we want to be as cool as possible to reduce the losses. It's not the same for the rotor. We have magnets. So in the low speed area, we want to have cool magnet to have the higher field density and have the highest torque, reduce the copper losses indirectly and the inverter losses. But in the higher speed region, in the field weakening region, we can make what we name a thermal field weakening. By making the rotor hotter, we reduce the field in the magnet, and therefore we need less current for field weakening and get a better efficiency. For the inverter, it's the same. They are mainly current-dependent losses, so we want to be as cool as possible. And finally, for the transmission, due to some hydraulics, I will not go in details, we want to be cool in high torque low speed, and we want to be hot in higher speed. So that's a summary of what I just say. So that means starter and inverter want always to be as cool as possible, and rotor and transmission, it's kind of torque and speed dependent to optimize the efficiency. So to look at this in our model, I also do an influence of the rotor cooling. So we can vary at two parameters, the oil temperature we consider and the flow rate. And that's, for example, the influence of the oil temperature. So typically we assume for the reference oil temperature of 75. And if we increase steadily the oil temperature, we can reach around 0.2% efficiency increase just by controlling the oil temperature. And on the other side, we can do the same with the coolant flow. So for example, assuming 4 liters per minute as a reference, if we reduce the coolant flow, we reduce the cooling of the rotor, we'll have a hotter rotor and control it on the driving cycle. and we can increase the efficiency. In this case, it's around 1%. So it's really important for us when we use the oil system. We have additional cost, but we have also potential to increase the efficiency of the system by controlling how we use this oil in the system. That's what brings me to my outlook, trend and technology for the future. So we now have this oil system, and we can use it on different levels. So we can use it on a machine level by controlling the oil pump. That's what I said before. We can control the rotor drag losses, also reduce the energy in the pump that we need. On the system level, we can use it for conditioning. So for example, in winter, you have in low temperature because your car stay outside for a long time. We can bypass, for example, the heat exchanger, increase the oil temperature, and reduce the losses in the bearing and the gear to have a better and smooth start. And finally, on the vehicle level, we can use what we name eAxle heating. So we can use the eAxle, produce some losses, extract them directly with the oil and put it back in the coolant system in the vehicle. And then we can warm up the coolant in the vehicle for the conditioning of the battery, and then don't have any range decrease in winter, for example, your battery is colder. And therefore, using this, we have a higher system integration and function, so we can already use the advantages of the oil cooling system to increase the performance of the vehicle. Thank you for your attention.
So also thank you for the presentation. And if anyone of you has a question?
Maybe I'll start, as I already have. Thank you. Very interesting. Very interesting. In terms of oil, so I think e-machines like oil. What I hear is batteries also like oil, dielectric cooling. The kind of odd one out is the power electronics. What do Bosch think about the future there? So, I mean, ideally, you want to have oil, one coolant.
So it's really, so the oil is worse for the cooling than the water. And then it's a concept, or you want to put oil directly on the chip, for example, in the power electronics. So it's a really critical topic. Also, in our case, as a supplier, we always get the water as an input. So even if we go on an entirely oil-cooled system on the e-motor, on the transmission, we still receive water as an input from the customer. So the water is there. It's really efficient to cool the inverter. We just use it. It's already there. We don't have to have a water pump and nothing. It's just coming from the customer. It's really efficient for cool the power electronics. So as long as it still be there as a boundary condition, it's easy to use it. There is always concept to go with full cool oil system, but that we will put even more pressure on the oil system because we need also to compensate for the inverter losses and so on. So maybe a bigger heat exchanger, a bigger oil pump. So as long as the water is there and it's efficient to cool the power electronic, I will say in the first assumption, it's still better to stay with water cooling.
Thank you. Can I ask a second one as well? For oil cooling, do you still need an oil-water heat exchanger?
So we are looking at different concepts. So we are also a concept where you're doing through the housing. So putting the oil near the water and having an exchange. The easiest solution at the time is to put a water oil heat exchanger and just do it because it's really efficient, really compact. You can do it through the housing, but you will need additional space. So it's at some disadvantages, yes.
Thank you.
Yeah, so I think the next presentation, so I have two questions regarding this. So I see you compare different cooling with rotor, stator, with oil, with water. So may I ask, all the comparison is done with simulation, or you have the physical test or validation on behind?
So in this case, we do it with simulation to compare only the cooling system, but all the cooling systems are based on measurements, so the simulation are validating, and we are using internal simulation tools to do it.
Okay, so may I ask maybe how it differs from the simulation to the physical test? So is that closer with each other, or?
So this model are validating, so we see kind of exactly the same result between measurements and simulation. Okay. It's already pretty good to estimate the real behavior of the system.
Okay, and another question regarding the efficiency between, you compare with different WLTC, and so I see the difference is really on the last digit, so 0.7, 0.9. So it's, I mean, the number is a little bit closer for me. So I'm wondering, so from the reality in the production, so does like this 0.2% or 0.5% difference on the efficiency really make the difference on the whole performance on the cost on auto?
That you need to ask the customer.
Okay.
Because 0.5% could be the difference between achieving the efficiency and not achieving the efficiency. So it's sometimes really small changes are really important. And here it's only the influence of the cooling system. If you put everything together on the system optimization, optimizing power electronic and so on, it's a huger gap. Here it's only the part coming from cooling system.
Okay, yeah. Thank you.
Thank you for this great presentation. And I would like to ask a more general question. You are using an interdisciplinary approach, and what was the most struggling part of this system?
For the simulation?
Simulation.
No, you mean what is the most struggling part? So we have a really good, I would say, simulation toolchain.
Yeah.
So we have already a multi-physics toolchain considering everything. So even in the system optimization, we already consider mechanical simulation of the e-motor, electromagnetic cooling. Everything is already in it. So there is no really struggle to do a study like this. It's just an example of the different influence.
And the second one, have you ever considered multi-phase motors more than 3?
More than 3-phase?
Yeah.
For passenger cars, we don't have the need currently. So there is some application for commercial vehicle looking at more than 3-phase motor because they require higher power and they will need higher current, so more than what you can put through 1 phase. But for passenger car, we are only looking at 3-phase current system currently.
Okay. Thank you.
Okay, thank you for the presentation. Then I would like to hand over. Can we do it like this, because we also lacking some time, that I encourage you to get together in the break and ask questions also